want to just see, are there any questions? Are there any types of problems that you want me to first start off with? Because I don't want to just work through problems, especially if it's ones that you already feel comfortable with. I want you to be able to have your questions answered, or whatever you came here for that I can help you with. If not, it's okay. I just want to at least open that up, that option up for any of you who have any questions or any problems you want me to work on first.
Can you do one where we have to try to find the U, like we put a few on top guessing, and then we have to pick which one we use?
Oh, okay. Sure. Yeah. So, I mean, we can, yeah, why don't we do this? Why don't we go through each of these problems, and let's just figure out the first step, right? If you can figure out the first step of these problems, then that's great. That means you are, because that's the hardest part. Getting that first step down is the hardest part. So yeah, why don't we do that? Let's go through each of the, let's go through our checklist, and you guys tell me how we should proceed. So starting with number one, we're not going to work through all the problems until, so let's do all the U values for each of them, or if there even is a U value. So first option is always expansion. Is this a problem that we can work through by expanding or moving things around?
We can't move things around because there's only a simple, or there's not a simple number in the denominator.
Right, there's not a single term, right? Good. Yeah, multiple terms, and we know we're stuck. Okay, so we know that expansion, power rule is out of the question. All right, now we're moving on to U-substitution, and we want to pick a U value. What do you think a U value could be?
One plus x to the 1/3.
Yeah. And I encourage you guys to, if you haven't already, encourage you guys to read through this technique checklist. I feel like I try to spell out as much as I can as you are working through your process. And one of the process is, if you're trying to pick a U value and there's already a parentheses staring right back at you, then that is probably a good place to look for your U value. Okay, doesn't mean that's going to work 100% of the time, but it is a good place to start. So the parentheses is there to help you, and so let that be your first. We should be drawn to that as our potential U value. Good. So these are going to be a little too small, not enough to make an impact, because we want the U value to be large enough that it can handle the remaining x's, but we also want it to work towards a specific rule, and the hope is that because U is a large part of the denominator and it'll take care of this, we should be able to work our way down to this 1 over U. Okay, we can work on these problems more specifically after we get a chance to start all these problems. Okay, all right, well, number 2 here. Can I expand, bring everything up, just use power rule? So similar to number 1, right? Too many terms. Okay, so expansion, power rule is out. What about U-substitution?
You could do U-substitution.
Say it again.
You could, I think.
You could. Okay, so let's consider it, right? If we let the U value be x squared plus 2, we're going to be left with 2x, and that 2x is not going to handle all of these terms up here. If we let the u-value be numerator, which already we know we're running into an issue because u-value in the numerator is not usually going to be a good fit. But even if we did, the derivative of x to the fourth will become 4x cubed, and we're not going to be able to get that matching part to cancel out. So yeah, this is not going to be something we can do with U-substitution. Degrees are not favorable for our u-value to choose. So what's our next option down then?
Long division?
Yeah, it's going to be a long division problem. So you know it's a long division problem. First up is multiple terms in the denominator. Second, you have degree. You have a basically a rational expression, right? Like a polynomial over a polynomial, kind of. And your numerator degree is more than, if not at least equal to the denominator degree. So those are all indications that we can potentially explore long division as a possibility. Can we do synthetic division for this problem?
No.
Okay, degree is too high, right? Only works if it's like x plus 2, x minus 1, x squared is too high. The only method we can work towards is long division. So okay, number 3, integral of secant x tangent x over secant x minus 1. Obviously not power rule. We can't expand because it's not even in the same category. All right. What about U-substitution? So maybe the U value is secant x. Maybe it's tangent x. Maybe it's secant x minus 1. Maybe it's the entire numerator. Maybe it's secant and tangent. All right. What do you guys think?
Secant x minus 1.
Yeah, it's going to be the entire denominator. If you're choosing between numerator and denominator, let's go with the denominator. And all these is going to be a little bit, it's not going to be quite enough. Remember, if you go with the U-substitution, ultimately, you want to pick the U value so that one of these rules appear, right? You're trying to get your problem to look like one of these integral rules, okay? And you can see them on the right here are all of trig rules available, and whatever it takes to get to that, to get to one of these rules is what we're after. And the denominator is favorable here because secant's derivative is secant tangent, so we should get that to work out. Okay, so numerator is not a good place to look. Secant or tangent alone is not enough. Okay. Okay. Number 4, can we move terms around?
I think that we can do power rule.
I think we can, okay, so we can move things around because there's only one term in the denominator, but it's not going to be power rule. However, we are going to explore the rearranging because this is only one term and the numerator and denominator, they all are within the same family. So we know that we can merge, right? It's not like e to the x and cosine up here. These are all kind of same family of functions. Even though it's not x algebraically, it is e to the x, so we can move that up. So let me just work this problem a little bit here. I like to, if I see only one term in the denominator, I realize it's helpful for students just to think of it as splitting up into multiple fractions. So if you clean this up, bringing to the top, changing the exponent, combining terms, you're left with e to the x, right? If you bring this up, it becomes e to the negative x. 2x minus 1x is x. This just cancels out. And then this e to the x, we have a rule for e to the u, but e to the u only works if it's in the numerator, so. So these two we can apply using e to the u rule, but this we got to be careful. That negative x is going to produce something other than just 1. And 2dx is just power rule. So yeah, let me finish this problem here. This is a little bit different. So e to the x, right? We can just do a matching of rules here. 2 becomes 2x. And then this is a little different. So our u value is negative x, so we know there's going to be something left over here. So I'm going to go to U-Substitution. Basically, it's e to the u, but there's a leftover negative 1. So that negative x is going to produce a negative 1, but we're going to get the same, virtually the same thing as this one, just with the negative in front. Okay, any question with number 4? E to the 3x over x squared. Can we move terms around? What do you guys think?
Yes, you can.
We could move that x squared, but once that x squared comes up, what do you notice? What's the issue?
There would be no denominator.
I'm sorry, say it again.
You wouldn't be able to like cancel it out.
Yeah, that's part of it. And also, if I were to bring this up, can I merge x squared and e to the 3x together into one variable?
No.
Right, so what I want you to be able to recognize is that these are two different families of functions. We're not going to be able to just remember from 4.1 where we can just put everything up in the numerator, distribute, clean everything up, rely on power rule. So as soon as you see two different families of functions, you know that it can't be a just expansion, even if there's only just x squared below. So we need to target U-Substitution here. So looking at these integral rules, these are the most common ones. What rule do you think we can work towards? What could be an end goal in terms of e to the u? Okay. So if you want to target e to the u, what does our u value have to be then?
I'm not sure.
Okay, so look at this here. If I want to use this rule, where does my u value have to live?
Oh, in the denominator?
Well, where's the u located in this rule here?
Oh, wait, actually, no, you're right. It has to be 3 over x, right?
Yeah, has to be the exponent, right? If you pick a u value that is any different location than that exponent, then you're matching a different rule, right? So if you know your end goal in mind and you're trying to decide what the U value is, follow that pattern, right? The only way I can get that U value to work is if it's up in the exponent. Now, it seems strange seeing this x squared down here, but you notice how your U value has an x in the denominator. So everything is kind of opposite with this derivative, and this will eventually work to cancel and deal with that x squared. Okay, maybe we'll come back to this one here. Okay, but I want to kind of give a preview for each problem here. Okay, what about number 6? Can we just push things up and rely on power rule?
No, you have to do U-substitution.
Yeah, what could be our U value?
1 minus 3x.
Yeah. And do you foresee a potential issue down the road with this process? This is right. This is right, but
Not being able to cancel out the x.
right. So you got to solve for x. Now this is a little bit on the difficult side. We'll probably give you one as messy as this, but yeah, that's the process I want you to go through, right? You decide whether you can expand. If you can't, use substitution. And if you still can't get the U value to take away all the x's, then you may have to rearrange this problem and replace that x in terms of U. Okay, so U sub with a change of variable is number 6. Yeah, but this is a little more more difficult than what you're going to see on the quiz. Just want to let you know. So don't worry about number 6. I just want you to understand that process, though. All right, number 7. Does it look like a rule that we can use?
Would it be the third rule?
Yeah. So it's close, but not perfect. So we got to go through U substitution, right? What's our U value?
X over 2.
Yeah. And the parentheses help, right? Parentheses kind of helps you see that connection there. All right, we'll come back to it. Number 8. Can we expand this? Can we move things around? Denominator has too many terms, right? Kind of stuck in this form here. So what about U substitution?
You could.
Okay, what's our U value?
1 minus 4 to the third x.
That's right. Yeah, you let the entire denominator be the U value, work your way towards 1 over U. You know that this derivative should be able to handle some form of that if we use our derivative rule for a to the U, which I have here. But yeah, denominator. All right, what about number 9? We can't merge anything together, right? You got an exponential here, you got a trig. So we got to go to U-Substitution. Do you see a rule that we can work towards for number 9? Do you see an exponential function in there? Now, where's the exponential function?
To the sine x.
Yeah. So do we have a rule for exponential function?
Would it be the log base of a rule?
Not log base of, well, no, that's the derivative, right? Just asking about the integral rule. What integral rule are we going to work towards here?
The bottom one on the
Yeah, this a to the u. Now things are a little out of place. It's not perfect, but if we rearrange it, we should be able to get this to match this rule. So we do need to rewrite this problem because things are a little out of place. It's not ideal for this because that 2 is not quite in the right spot. So what would this look like if I push that 2 to the numerator? Can I write an equivalent expression with the 2 in the numerator? Or what happens if I flip this 2 up top? How can I do that without changing my overall expression?
make it a negative.
Yeah. So this is a rewrite of the problem. Now it's a little bit easier to spot, right? Okay. What's our u value here? Any ideas?
Negative sine x.
Yeah, there we go. Negative sine x is our u value. Derivative will handle this, and we should be on our way to working towards that that form. All right, so now that we've tackled the first step of every problem, let's go back and see if there's any that you want to work out in detail. Okay, we did number 4. All right, is there any of these that you want to see worked out?
I don't have a specific one, but could you just pick like one that's most similar to what you think would be on the test tomorrow? Or like the most common one on the test tomorrow?
Yeah, there's different versions out there, but there's going to be one long division / synthetic division. There's going to be a U-substitution involving natural log. There's going to be e to the u. So.
Could we do the long division problem then?
Okay, all right, let's do this one here. So we have to do long division here, right? That x squared is a little high. So all right, so first things first, x squared times what gives me x to the 4th? x squared, right? So I put x squared up here. And I think it's helpful to protect your divisor with a set of parentheses so you can remind yourself to distribute that through. X squared times x squared is x to the fourth. 2 times x squared is 2x squared. Okay, we draw our line, we change our signs. First term always matches and cancels out. The rest, we got to be more careful because not all of these are like terms, so we're going to bring them down by descending order. Back to the start. X squared times what gives me negative 2x squared?
-2.
Negative 2. Now we're done with the x squared, so we don't care about this anymore. We'll just take the negative 2 and distribute it through the x squared plus 2. Draw our line, change our signs. Conveniently, not only does the first term go away, but also the last term, so we're only left with x. Okay, can I keep going here?
Yes.
Can I multiply x squared by something to get to x?
Oh, no, you can't. I don't-
Right, so drop it. Well, as soon as it drops below the divisor, we stop. Okay, it's a little too low. So we call this the remainder because we can't divide any further. Now with long division, we haven't solved the problem, but what we have done is we've created an expression that's the same as the original problem, but just easier for us to identify integral rules. So I'm going to use the space here for number 1 to finish this problem here. So we'll take this x squared minus 2 plus x over x squared plus 2, and we'll just understand that we now have to find the appropriate integral rule for each of these terms. So what rule do you think we can handle these two terms with?
Power rule and U-Substitution?
Yep, these both are power rule, and the last one is U-Substitution. Okay. So these are easier, right? But if I want to go through U-Substitution here, this is kind of like a standalone problem here. What's our U value then?
X squared plus 2?
Yeah. Yeah. Okay, we go through that process. Clean this up. So when everything is said and done, x squared becomes x cubed over 3. 2 becomes 2x. 1/2 1 over u becomes 1/2 natural log. And I'm just going to go ahead and replace the u back in terms of x. There's our answer. Any questions with the process for number 2? Okay, U-substitution, canceling out. This will be 1 over U. This will also be 1 over U. So I think these are pretty straightforward once you can work your way down to the derivative. Anybody still need to look at 2? All right, let's look at number 5. I think number 5 is a good one to look at here. We identify the U value, so let's continue that process. And we do see bounds in this problem, but we're going to work this problem without the bounds first. Right? The bounds come at the end. We know to target the exponent and the dx. All right, so how would you find the derivative of 3 over x?
Bring x to the numerator.
Good. We got to do power rule, but to do power rule, that x has to be in a better spot. I mean, you could leave it down here and go through quotient rule, but I think it's faster just bring it up and going through power rule. Now, we can't just treat that x and just call it 1, right? This is not in the right place, so you got to bring it up first. Now we can find du dx. All right. There's power rule. What's the derivative of 3x to negative 1?
-3.
Go through the full power rule here.
Oh, wait. Never mind.
What's that going to be? Anybody else? What's the derivative of 3x to the negative 1?
Wouldn't it be -3x to the -2?
Right. And as you're saying that, you set to the -2 and you see x squared here, so that's a good sign, right? Where we know that that 2 is going to be potentially helpful for this x squared that needs to be resolved. So initially, it didn't quite look like this u value is going to be able to be enough. But the fact that it's in the denominator, and we got to bring it up, and that -1 exponent turns to -2, we can kind of see how this derivative is going to pair up with this, right? The field doesn't quite look like it's going to do it, but it's able to do that now. -3x to the -2. Okay, we still got to go through a little bit of cleanup process, but at least we have something that's a good sign. I'm going to clean this up a little bit. I just like to work in terms of positive exponents, especially when I'm trying to do some cleanup. So try to get that dx by itself. Okay, divide. And substitute. So this is going to go in place of dx. My exponent gets replaced with u. And let's see how things look after that. All right, what do you guys see here? Can we work towards this rule? What would you do next to clean this up?
Cross out the x squares.
Okay, good. What else?
You bring a negative 1/3 to the front of the problem.
Good, good, good. All right, so once you do that, it's a very clear indication that we can apply the rule in front of us. Integral of e to the u is just e to the u. And final step, replace the u back in terms of x. Oh, I forgot something. What are we trying to achieve here? We still got to worry about what?
The
The
interval.
bounds.
The bounds. Okay, so two methods, right? We don't have that plus c. I'm going to bring the bounds back into the problem here. We have 1 and 3 being our lower and upper bound. So you can choose which method you want to do. I'm going to do both methods and you let me know if you have any questions. First method is leaving our antiderivative in terms of u, and which means that these bounds need to be adjusted because right now our bounds are not in terms of u, it's in terms of x. So I know I got to place some values there, but I'm going to have to do some conversion. And my conversion is stored in this expression we started with at the beginning. That's how we convert from one variable to the other. So if x is equal to 1, then u is equal to 3 over x. So that means u is equal to 3 over 1, which is 3. My new lower bound has been transformed to be 3. And my new upper bound is now 1. I know it seems strange, but we can just go through this process, right? Doesn't matter if these numbers look out of order. Just follow that process. Careful, when you see this minus sign, it's top expression minus the bottom expression. And there's already a minus sign here. We got to keep track of our minus here. So there's going to be another negative. If you leave your answer like this, I'd be okay with it. But I'm just going to clean up a little bit. So this is perfectly fine. Oh, forgot the negative. Okay, that's method 1. Method 2 is where you go one step further. You bring that e to the u in terms of x. And then you work in your original bounds. And you get the same answer. Okay, any questions with that process? Let's do number 7. think we already said our u value is going to be x over 2. And we already had a match for the rule that we want to use. Hey, what's the derivative of x over 2?
One half.
Yeah. So maybe it's easier to rewrite this as 1/2 x. If you do, it's a little bit easier to spot that derivative is just going to be 1/2. Yeah. Cross multiply. We substitute. And we can apply our rule here. Okay, push the 2 out in front. And now I got a perfect match. Apply my integral rule. And get our x's back into our answer. Any questions with 7? I want to point something out here. Look at the u value. What pattern do you see in terms of, I mean, I want you to be able to see this pattern for kind of relatively easy, simple u terms where it's not very complex. What do you notice about the u value and what's produced as a leftover? What's that relationship? Anybody want to take a guess? Or what's the relationship between 1/2 x and 2? So you can go through this every time. I just want to point out that there's a bit of a shortcut that you can do, especially for U-substitution that are relatively simple, is that we're doing the opposite of chain rule. So normally when you do chain rule, you just multiply by the derivative. But here, with integrals, we're doing the opposite, and so we still get that kind of that derivative portion to show up, but now that derivative is going to be the reciprocal. So if you can see that pattern, then you can jump from here directly to here. I mean, assuming that you can see that rule there without having to go through these additional writing of u and keeping track of all that. So that makes for a speedier process, once you're comfortable with that. So let me just show you another example where we can jump to that conclusion without having to go through a bunch of rewriting of problems. So let me do another problem that looks like a rule that we can use. Do you see how this cotangent matches nicely with this cotangent rule? So you know that it's basically because it's going to be natural log of sine of 5x, and we got to keep track of some coefficient, right? So maybe you want to take a guess what the coefficient is going to be without having to go through all that rewriting of U-substitution, which we could, but just want to hope you see that pattern.
Would it be 1/5?
Yeah. So if you can see that pattern, then you can just jump directly to the antiderivative without having to write a whole bunch of stuff. But we do need to understand that it's the reciprocal, right? It's not 5. It's not times 5 because this is antiderivative. There's going to be a little bit of an adjustment. But, you know, we can save quite a bit of time. And I'll be perfectly fine if you are able to jump from here to here and not go through U-substitution. You understand you are going through U-substitution, but then you're just pulling that, you're identifying that pattern and you're adjusting quickly. So just want to give that option. So let's do another one. Let me give you this one here. What if it was can you jump to the answer without having to do a whole bunch of U-substitution? Any ideas?
Is it 3/7?
Yeah. Okay, so can you finish that out? What 3/7 is definitely part of it, but what would the rest of it look like? Anybody want to finish that? Because yeah, that's the hard part. The hard part is understanding that there's going to be a 3/7, but how would you write your answer then? So, all right, I'm just going to follow the rule here. I see a negative. The 2 is going to have to be part of my answer. That 2 is not going to have any impact except for the fact that it's going to have to tag along to the answer. So let me just start off with this. I'll put a -2 to begin with. You know that 7/3 is going to produce us 3/7. So those are all the numbers that we got to keep track of, right? After that, we can jump directly into the rule. So natural log of cosecant of u. I know my u value is 7x/3, so I can just copy that. Leave it like this or clean up a little further. Yeah, save a little bit of time. Jump directly into the answer. Just have to do a little bit of adjusting there, but we can save a lot of writing if we understand the process. Okay, any other questions? Okay, I encourage you guys to work through the rest of this review sheet and take a look at the morning review. The mixed review I think is also good, but it's gonna be 6 questions, kind of one of each type that we've focused on in these 3 sections. But I'll have a morning review tomorrow, 7:15 as well. Thanks, guys. See you tomorrow.
Thank you, Mr. Yang.
Uh-huh.
Thank you.
Bye. Thank you.